Medial triangle. Now, this is going to be exercises with similarities of triangles. So I want to remind you that in the last video, we proved two important features of two important criteria for proving that triangles are similar. In particular, if they obey the side similarity criterion, that is, if their sides, if two triangles have sides which are proportional in the way that they would be if they were similar, then that implies that they're similar. Also, if two out of the three sides are in relation to a different triangle are proportional, and if the angle that connects those two sides are equal, then that's enough to show that two triangles are going to be similar. So here we're talking about the medial triangle. So let me remind you what the medial triangle is. Supposing we have a triangle ABC, and we're going to create its medians. Now the medians are the Chevians that go to the opposite sides. So all we're going to do here is we're going to construct the midpoints, D, E, and F of the sides of the triangle, and then we're going to connect the dots to the opposite sides. Now here, this produces the intersection of the medians, which, if you'll recall, is called the centroid of the triangle. But that's kind of not the point right now. What we're going to do right now is we're going to connect the dots further to create this inner triangle DEF. And this inner triangle DEF is called the medial triangle. Now, as you'll notice here that I can move this, and the medial triangle kind of stays with the triangle in that way. So if we have medians AD, BE, and CF, and medial triangle DEF, then the first claim that we want to justify here is the claim in the second line here. The medial triangle divides the triangle ABC into four half-sized triangles, all of which are similar. So what I'm going to do is I'm going to hide these medians so that we can focus on this situation here. Now, those all look similar, right? I mean, this looks AFE looks congruent to FBD, looks congruent to EDC, and in fact looks congruent to DEF. That's what we want to show. We want to show furthermore, not only are they all congruent to each other, but they're all similar to the original triangle. And it's quite believable in this picture. AFE is just a half-size version of ABC. That's what we want to prove. Now, it's surprisingly hard in this picture because we know surprisingly few angles as we start off. The point F, for example, is the midpoint of the segment AB. It divides it evenly into two segments. That doesn't tell us what this angle is, or this angle, or this angle. The point D divides BC into two equal segments. Of course, the size of those segments doesn't need to be related at all to the size of AF and FB, but it divides it evenly into two segments equal to each other. But again, that doesn't tell us anything about these angles. So we know almost nothing about these angles up front. The only thing we really know, and it's more or less trivial, is that a triangle ABC has an angle in common with triangle AFE, right? Namely the angle A, right? The angle A is certainly in common with both triangle ABC and this smaller triangle AFE, which I think I will shade so that we can focus our attention on it here. So let's focus our attention on triangle AFE in relationship to ABC. So certainly they share this angle. We don't know that this angle matches this angle. We don't know that this angle here matches this angle. Now you might say to yourself, well, look, we've got parallel lines. And whenever we have corresponding angles with parallel lines, then nice things happen and this angle will be equal to this angle. And yeah, you'd be right to say that. We do have parallel lines. The line BC is parallel to the line FE, but we haven't proven that yet. And it doesn't follow in any obvious way from the fact that we've created these lengths. So that's kind of something that we still need to prove. And so we can't use the parallelism of these lines to get the angle equality. What can we use? Well, we can use the similarity criterion. We know that the ratio of AB to AF is exactly a ratio of 2, or 1/2, depending on how you divide it, right? This is a 2-to-1 ratio between the length AB and the length AF. Why? Because F is by definition the midpoint of the segment AB. We know similarly over here that the ratio of AC to AE is a 2-to-1 ratio. And so we have the ratio of these two sides, AF against AB, compared to the ratio of these two sides, AE against AC, they agree in ratio. And so that is the side and the side in the side angle side similarity criterion. We have an equality between the ratios of the sides corresponding on this side and the sides corresponding over here. So We also need the angle, but the angle is the shared angle at A. And so basically what we're saying is that AFE meets the side angle side similarity condition for being similar to the triangle ABC. Now, if it does, then it must be similar. And what do we conclude from that similarity? Well, a lot of some importance. So what we conclude from that similarity straight away is that this angle F here, this angle AFE, must be equal to this angle B. So I'm just going to shade it here. This angle AFE is in fact equal to this angle ABD, or ABC, same thing. So, and you can see that GeoGebra is measuring them equal, but having them measured equal is not a proof, right? We're calculating, we're giving a proof that these must be equal. Now, what else can we conclude? Well, that's this angle. We also said that since AFE is similar to ABC, then we get an equality of these angles. Now, that doesn't mean all four angles are equal, of course, but it does mean that angle FEA is going to be congruent to angle BCA, or DCE, same thing. So, and you can see here that GeoGebra is measuring them equal, but we don't need to have that measurement. We can just say, because we've proven that they must be equal, right? So we can trust that these are equal because we've proven that the triangles are similar. Now, what else is going to be equal here? Well, we've got, so this is one way of looking at this picture, comparing this triangle to the others. But there are lots of other triangles that compare exactly the same way to the original triangle. This is another one, and this is another one. And so from these, we get all kinds of other angle equalities. We get this angle here at F is congruent to angle A. This angle here at D is congruent to this angle C. This angle here at E, the angle DEC, is congruent to, again, angle A. And this angle here is going to be congruent to B. So we get all kinds of angle congruences here. And I'm just going to measure some of them so that you can see that, yes, indeed, they're all ending up equal to each other. So we get lots of them equal to angle C. Here's another one which is equal to angle C. And then we get one up here, which is also going to be equal to angle A. So let's measure that one. So basically, we get all of these angles that point sort of downward in this picture are congruent to angle A. All of the angles that point, sorry, there's a left-right reversal, which is confusing me. All of the angles which point leftward in this picture are congruent to angle C. And all of the angles that point rightward in this picture are congruent to this angle B. Okay, that gives us the parallelism, which I said before we don't know, right? Now we know it. And the reason, I'm going to hide some of this stuff. The reason this gives us the parallelism is because once we get the angle equality here, that forces these lines to be parallel. So by all those angle equalities, we can say, okay, now the lines are parallel. So what have we got here? We've got we've got three triangles, each of them congruent to the original triangle ABC. I haven't addressed the middle triangle. And you might think, well, the middle triangle is really very different, isn't it? Well, I mean, yeah, I suppose that it is different, but it's not much extra work to identify that the middle triangle is not only similar to ABC, but it's similar again at this 1/2 ratio. There are a lot of ways to go about this. Let's do it using a side level thinking first, and then I'll suggest a completely different way of working it out. So thinking about its sides, the first triangle we talked about, we used the side angle side to identify that this triangle is similar to ABC. But once we have identified that it's similar, then all of the sides in relationship to those of ABC have a 1:2 ratio, including this last one, EF. That means that EF must be exactly half of BC in length. Now, that's what we learn about that triangle. When we made the similar reasoning about the next triangle, we can use a side angle side to reason that this one is similar to ABC as well. This in relationship to AB is 1 to 2 ratio. BD in relation to BC is 1 to 2 ratio. This is exactly half scale. And that shows us that DF is exactly half of AC. And then finally, when we consider the third polygon, this, this length here, for the same reason, must be exactly half of the length of AB. And so putting all that together, this is half AB, this is half AC, and this is half BC. So these sides are in a 1 to 2 ratio with the sides of the original triangle ABC. And therefore, by the side criterion for similarity, this inner triangle must be similar to the original triangle ABC. And there you go. We get 4 half-size triangles. And by half-size triangles, I mean literally similar triangles whose similarity ratio is exactly a 1 to 2 ratio. There's another way to get this medial triangle similar, and that is to think about angles and adding up to 180. You see, this angle is basically angle B here. This matches angle B. This matches angle A. And this, whatever it is 180 minus A minus B. But we have ABC in a triangle here. 180 minus angle A minus angle B has to be angle C. So this one has no choice. It has to be angle C. And then this one, by similar logic, has to be angle B. And this one, by a similar logic, has to be angle A. That alone will get you the similarity between the medial triangle and the original triangle. However, that's not all it's cracked up to be. That won't tell you the scale. From that logic alone, we can't deduce that it's a 1 to 2 ratio. So the prior argument might be favored here for showing that this inner triangle is similar to the triangle ABC. Okay, what's next? I already discussed the parallelism. If this angle actually is equal to this angle, if angle AFE must be equal to angle ABC, then that means that this line here, so this is a straight line, of course, then this line must be parallel to this line. So the sides of DEF are parallel to the sides of ABC. And now I think I want to remove a whole bunch of angle measures, which we probably don't need anymore. Then I want to discuss the relationship, well, something interesting that happens with the circumcenter of this triangle. So this is, notice this point G here that I've marked, I'm going to leave it, but that's the centroid, that's not the circumcenter. Now I want to talk about the circumcenter of this original thing. So what is the circumcenter of a triangle? It's the center of the circumscribed circle. How do you construct it? The best way, the simplest way to construct it is to find the common point of intersection of the 3 perpendicular bisectors of the sides. So I'm going to use the perpendicular bisector tool, and I'm going to just click the side, which is the side BC here. When I click this, it will not interpret it as BD. It will interpret it as BC, if I'm lucky, yes. So now I've calculated the perpendicular bisector. Why did it pass through D? Well, this is not a coincidence that it passed through D. D was constructed in order to get the median, but it was constructed as the midpoint of BC. So of course the perpendicular bisector passes through the midpoint, right? When I use the same perpendicular bisector tool on the segment AC, it passes through E, no surprise. And when I use the same thing on the segment AB, it passes through F, okay? Now we've already shown in a different video that these 3 perpendicular bisectors intersect, and their point of intersection is called the circumcenter of that original thing. So I'm going to try to get that thing to relabel itself. Having a little trouble with the interface here. So let's get that thing relabeled. I want that to be O, which is a more standard symbol for that circumcenter. Okay, so now we have the circumcenter and it's labeled O. And if things look a little crowded, then I can adjust the shape of the triangle so that things look a little bit less crowded. I don't want it to look like an equilateral triangle. If I make this look like an equilateral triangle so everything is nice and symmetrical, then I won't be able to tell what's going on. So I want things to be a little bit lopsided so that, for example, I can tell the difference between my circumcenter and my centroid. All right, what's this all about? I'm advertising a relationship here between the circumcenter of ABC and something going on with DEF. And so let's just think about it abstractly. I have produced the circumcenter of ABC by creating perpendicular bisectors everywhere. Have I thereby created the circumcenter of DEF? Well, no, because this line is not a perpendicular bisector of EF, right? EF has its perpendicular bisector. I can construct it if I want it. It's there. that's kind of not the point right now. The point is that this line that I've already constructed is not the perpendicular bisector of EF. Neither is this line here the perpendicular bisector of ED. Neither is this line the perpendicular bisector of DF. But they do appear to be perpendicular to those lines. Is that a coincidence? No, that's absolutely not a coincidence. We've just shown that line EF is parallel to line BC. And if this line, which is the perpendicular bisector of BC, is actually perpendicular to BC, then it must be also perpendicular to anything parallel to BC. In particular, it must be perpendicular to EF. So these lines are not perpendicular bisectors of the lines in the triangle DEF, but they are perpendicular to those lines. So, well, what are they? They're perpendicular to those lines, and they don't bisect them, but they do pass through the vertices of the medial triangle. Well, there's a name for that, right? A line that passes through one vertex and makes a perpendicular with the opposite side, that's called an altitude, right? We like to think of like this might be more easily recognized as an altitude if the picture were upside down, but this is through this vertex and perpendicular to the opposite side, so that must be an altitude. And that means that these lines, all of them, play a dual role in this picture. Yes, they are perpendicular bisectors of ABC, rather of the segments AB, BC, and CA. They are perpendicular bisectors of those, but they are also altitudes of this smaller medial triangle DEF. And that makes this one point, the point of intersection, simultaneously two different things. This point of intersection O is, yes, the circumcenter of the original triangle ABC, but it is also the orthocenter of the medial triangle DEF because it is the intersection of those altitudes.